Let's talk about how to compute the volume of a solid with a given cross-section that's not a circle. So this is still using what we were calling the disk method in section 6.2, but it's not for a solid of revolution. So problems of this type will look like what you see here. The base of a solid is this region I have in blue. So it's enclosed by y equals x squared, the vertical line x equals 2, and the x-axis. We're not rotating this region about any axis. What we're told instead is that cross sections cut perpendicular to the x-axis are squares. So essentially, like, all we know is that this is like the footprint that this solid makes. So if we cut perpendicular to the x-axis, that would be this way. So if we cut at some particular x value, and we kind of crack open the shape, apparently what we'll be looking at is a square. So here, squares are playing the role that circles typically do. So we still need to find a formula, like a function of x that gives us the area of that cross section, and then that's our integrand. Okay, so what we're imagining here is that this line I drew, perpendicular to the x-axis, is one side of a square. So the square is like standing up off the paper towards us. So if we turned it, what we'd be looking at is a perfect square, where one side of it is the height from the x-axis to this curve right here. So that height is this height, and as a function of x, it's the y value of this point on the curve. So the y value is x squared. Okay, so the area of a square is always the side length squared. And here the side length is x squared. So that means our area function is x to the fourth power. So then our volume is the integral of x to the fourth power. And we're going to take all of the x values we would need to hit every cross section, which is 0 to 2. So essentially, all that's different from this, as opposed to rotating this region about the x-axis, is that we're not taking this length and putting it into pi r squared for a circular area formula. We're putting it into side length squared for a square area formula because of this weird information. To compute from here, you would do antiderivative, plug, plug, subtract. That part I'm going to leave up to you because in this video, we're more concerned about how to put it together. All right, it is also possible that instead of squares, they give you a different shape. Squares are by far the most common option you see. The other one you might see is a semicircle, like the top half of a circle. In that case, you kind of attack it the same way. It's just you're not using the formula for the area of a square. You would switch to the area of a semicircle instead. So you're assuming that this is the base of a semicircle coming off the page. So the area of a semicircle is 1/2 pi r squared. And then the radius of this semicircle is half that distance. So I would take half the x squared distance. Right, so if we simplify that, we have 1 over 8 pi x. Oh, wait, that should be squared. So 1 over 8 pi x to the 4. So in that case, the volume would be the integral of that function instead. So we're just switching the area formula that's playing the role of integrand for solids of revolution, it's always a circle. If it says square, it's a square. If it says semicircle, it's a semicircle. All right, the one other wrench they could throw in the system is the type of problem you see below. So I'm starting with the exact same fairly simple two-dimensional region. Same setup exactly. This is the base of the solid. But now it says cross sections cut perpendicular to the y-axis are squares. Perpendicular to the y-axis would be this way. So now this is one side of our square. So what that changes is that clearly we would have had to pick a y value for that slice. So we're going to integrate with respect to y for this one instead. So we have to take a couple of different precautions, but otherwise it works the same way. At any given y value, I'm going to need the x. So I'm going to back solve this equation. Instead of y equals x squared, I'm going to say root y equals x. I'm only using the right half of that parabola, so I don't have to worry about a plus minus. Okay, so we need a formula for the area of that square. So let's say this is the whole square. That length is one side. We know that area is side length squared. So we say, all right, well, in terms of the y value that I'm at, what is this length? And this is a little extra tricky, right? So if we just say root y, the x value of this point right here, what that gives us is this distance here, root y. So it's the x value of that point is going to be the distance from 0 to that x value. What we want is the other part of it up here. The key here is that these two chunks together should add up to 2 because 2 is the edge of this shape. So what I'm saying is that 2 is root y plus the side length that we need. So the side length is 2 minus root y. And that's the integrand that we will use. So our volume is 2 minus root y squared dy. And then for this, of course, we have to integrate, the bounds of integration should be the y values that would make all the cross sections. So now we'll go 0 to 4. And that's it.